Okay, so our second talk is by Karim on Markov process leakage. Take it away. Floor is yours.
Thank you for the introduction. So my name is Karim, and I'll be presenting our work, Maple, which is a Markov process leakage attacks against encrypted search algorithm, which is just, you can view it as an extension of what Zishan just explained. So how do we leverage leakage in order to mount an attack to gain more information about the queries and also the plain text data. This is a joint work with Sirin Kamara, Tarek Motaz, Jamie Di Maria, Andrew Park, and Amos Tribe. So the agenda of this work would be basically me trying to motivate a little bit the need of for encrypted search, then a high-level overview of encrypted search algorithms. Then I'll pass to explain what are leakage abuse attacks against encrypted search algorithms, and then dive a little bit deeper into our two attacks, mainly attacks against the query equality leakage pattern in the dependent setting. And then I'll just gloss over some of the summary of our results, explain what the data sources that we used, and also the evaluation scenarios, and give you guys some key takeaways. So as you all guys know, in the past couple of years, data breaches has proliferated, and we are going to see, for example, each week some headlines like 10 billion passwords have been leaked, or for example, the mother of all data breaches where 26 billion records have been leaked, etc., etc. And this kind of leakage or data breaches affects a lot of companies and also users, and some of them are major companies, for example, LinkedIn, Adobe, Tencent, Weibo, X, among others. So the general idea, or ideally what we would like to do, is to have some kind of cryptographic mechanisms on top of our data prior to outsourcing it. This would save basically our data in the case of a data breach or a data leakage, but in the same time, if we just put a normal kind of cryptographic mechanism, we would lose our computational complexity over the data in the server because it's encrypted, and we can't just keep downloading our data each time that we want to execute some sort of computation over our data. So here comes to play encrypted search algorithms in general. So what is encrypted search? It is a research area that focuses on the data design, analysis, and implementation of cryptographic primitives that allow the user to query their encrypted data privately and also efficiently. At a high-level idea, I won't go over a lot of the details since Zichin already did that. So we have like a trusted client that would like to outsource their data. They can generate an inverted search index and then outsource the data to the untrusted server. And at any point in time, we can generate variable types of queries, either keyword queries, range, and other types of queries. And the server will send us the matching records to the client. And however, most efficient encrypted search leakage algorithms or schemes leak some form of information through the setup and also while executing the queries. And this is for the static data structures. And also we leak more in case we have a dynamic data structure where we can leak also the update and delete histograms. So for our work, we are mainly focused on a leakage that is commonly associated with structured encryption algorithms, where we have an attacker or an adversary that tries to mount an attack, given auxiliary information in some leakage to gain either the queries or retrieve the queries or the plain text data. And our adversarial model is a passive and persistent adversary. This adversary is basically, you can view it as has access to the transcripts of the execution of the protocol, but won't deviate from the protocol specifically or try to inject some kind of information. And given the fact that leakage and auxiliary information heavily influences the recovery rate of the leakage abuse attacks, I'll try to explain what is a leakage profile and explain why did we specifically pick the query equality in the dependent setting. So a leakage profile is a set of one or multiple leakage patterns. For example, we can have the response length or the query equality, co-occurrence metrics, among others. This is not a full set of all the possible leakage pattern, but just to give you a high-level idea. And we picked the query equality leakage pattern in the dependent setting because first, query equality is a leakage pattern that is leaked by most PPE and SSE-based schemes. And also, it hasn't been properly studied prior to our work. And we picked specifically the dependent setting because as a human, we are most likely than not to generate queries dependently. So let's say a person is sick or has a a stomachache, the first thing that you would do is look up their symptoms online and then try to find the nearest doctor, let's say, for example, a gastrologist in their area, or maybe if the symptoms are not that severe, they will just try to look for some remedies, etc., to stop the pain. So our main research question that we try to solve using our paper is this. So given observed leakage in a non-query distribution, what is the query sequence that is most likely to explain this leakage? And we try to do that given this adversarial model. We have an adversary that has access to the query sequence or the query distribution as its auxiliary information, and then the query equality pattern as some observation. Then we formulate our query recovery as an uncovering problem, and we use solutions from existing literature in the stochastic processes. Mainly, we model our query distribution as a first-order Markov process, Markov chain, and we use transition matrix, initial distribution, and stationary distribution as input for the Viterbi algorithm to solve this kind of problem. And to give you guys a high-level idea of our contributions, we propose 2 new attacks. The first one is the stationary, which you can view it as a frequency attack, where we try to basically match the average number of visits to the closest number or value in the stationary distribution. At a high level, this is a mapping of every query to its corresponding keyword using the convergence of the average number of visits. And for our second attack, we use the first attack as a warm-up, and then execute an inference attack where we model the user's query distribution as the hidden Markov chain from a hidden Markov model, and then the corresponding leakage as the observable process. More specifically, I'll just try to explain at a high level the steps that we do for our first attack. So the first step would be to compute the stationary distribution. Then we calculate the histogram of sequence of queries. And finally, we try to map the closest value in the stationary distribution to the average number of visits for all states. And also, our algorithm also outputs an error, which is the total distance between the average number of visits and the selected component in the stationary distribution. And as I just described in the previous slide, we use the first attack as a warm-up for our second attack. So from lines 1 to 5 in our pseudocode, it's just running our first attack. And for the second step, we compute the observation matrix from the hidden Markov model parameters. And lastly, we try to given the hidden Markov model in the observed sequence, we can run the Viterbi algorithm, which outputs the most likely sequence of visited states in the hidden process. And also, we output an error score, which is used to quantify the quality of our mappings. And finally, to evaluate our attacks, we use 2 kinds of distributions: a real-world query distribution based on the AOL entire data sets. And we also designed 4 evaluation scenarios. The exact scenario, it's a scenario where the adversary has access to the exact query log of the user. And the all scenario, it's another scenario that's more similar, but where the adversary has access to the query log of the client among other query logs. The split scenario, we give the adversary half of the original query log as training data, and the other, we basically have a set of query logs excluding the one that we are trying to attack. So you can view them as the first 2 evaluation scenarios are the most unlikely or most unlikely scenarios to happen in real life, but the second 2 are the most true to what would you guys can face in reality. And since we know that both our data sets can't cover everything, so we also try to execute our attacks over artificial query distributions, mainly for uniform zip and binomial zip and zip, where we varied the sparsity of the transition matrix. And I mean by that we varied the Hamming weight, which is just the number of outgoing edges from each given state. Finally, I'll just gloss over the summary of our results. As you can see, our attacks achieve a higher recovery rate for the first 2 evaluation scenarios, but none of the attacks really achieved anything or recovered anything for the second 2 evaluation scenarios. And this was true for both the AOL and TER datasets. And this is given the aggregation of the evaluation or the evaluation and result of our results over 5 users. Similar conclusions can be drawn also for the artificial distribution, where basically we had near perfect recovery rates if we fix the Hamming weight. And I mean by that, if we fix the Hamming weights to 2, which is basically we are having a sparse the transition matrix, and we vary the sequence length of the query sequence. But in the case where we varied the Hamming weight or we had a more dense transition matrix, our recovery rate started to drop tremendously to the point that we couldn't recover more than 15% after 100 with the Hamming weight equal to 100. And similar conclusion can also be drawn for the remaining artificial distributions, the binomial Z uniform and Z, etc. And to conclude, I would like to say that the recovery rate of existing attacks depends highly on prior assumptions over query in data given specific leakage profiles. And despite outperforming the state of the art, it is fair to say that none of the attacks really worked in a more realistic setting, and the computational overhead of all of the attacks, ours included, is really prohibitive in practice. And this can be seen basically here, where we varied the query sequence length. So once we started reaching 1,500 states per query sequence, we couldn't basically evaluate our data because each data point took us at least 4 hours to evaluate one data point for given a high-level servers, basically. And finally, I would say that it remains open to find attacks that work where the attacker does not know the exact query sequence of the user. Thank you so much, everyone, for listening. And for more details, please check our paper.
Thank you for the talk. Any questions? Should I start with one then? Well, let's start with a simple one. Why did you decide on a first-order Markov process and not something else?
Oh, we can use anything, basically, to model our query distribution. We just picked the Markov chain of the first order because it was the simplest kind of Markov process to do. But also, we tried to have as little information for the adversary as possible. So that's why we picked an adversary that has knowledge on only the previous step instead of having multiple steps. But it is possible to modify our results and have a Markov chain of order n.
Okay, any more questions now? There you go.
I was curious, following this. Of course, if the overhead is already huge, this is mostly theoretical, but
Yeah.
do you think it would change a lot if you have a second, third order Markov chain? Do you think it would be much more effective or
We tried, when we were having our evaluation, we tried for the second and third orders. We didn't see much of a change, at least based on a small query sequence. So we've already reached a high level recovery rate. So we had 100% in sometimes and sometimes 90%. So the average would be at least 70, as you can see here. So, but the problem that we faced is basically the longer this query sequence, that's the bottleneck that we faced. The longer the query sequence, the more problems we had. And most of the previous evaluations or previous work stopped at just 500. So we were the first ones to extend our work to more than roughly 2,000 query, the query sequence of the size of 2,000 states. So, yeah, sure.
Thank you. And next speaker can already set up while we thank him for the nice talk and the answers to the questions.